All right then, let's start chapter 2, monotone operators and base splitting schemes. In this chapter, we'll introduce the machinery of monotone operator theory, and we will present one main rubric. And so here's what this rubric is. We will use monotone operators and base splitting schemes to derive and analyze a wide variety of classical and modern algorithms in a unified and a streamlined manner with this unified rubric. And the rubric is as follows. In step 1, we'll pose the problem at hand as a monotone inclusion problem. So often, most problems that arise in engineering and science are not already in the form of a monotone inclusion problem. So what we will do is, for our purposes, we are specifically interested in optimization problems, both constrained and unconstrained. So we will take those optimization problems and then we will convert them into a monotone inclusion problem. Then in step number 2, we will use one of the so-called base splitting schemes to encode the solution as a fixed point of a related operator. So we transform the monotone inclusion problem into a fixed point problem. And then in step number 3, we'll find the solution with a fixed point iteration. So this 1, 2, 3 step is the rubric through which we derive and analyze optimization algorithms using the machinery of monotone operator theory. And you'll see this idea repeated throughout this chapter and actually throughout the entire book. Okay, so let's first introduce the mathematical tools needed to carry this out. So let's define the notion of set-valued operators. We say T is a set-valued operator on Rn, and we write it in this way. So T maps from Rn with a double arrow to Rn. So usually when you define the domain and the range of a function or an operator, you do so with a single arrow. But here, instead of using a single arrow, we have a double arrow. And this double arrow is used to denote set-valuedness. And what it does, what this type of operator does, is that it takes in as input a point in a vector in Rn, and then the output of the operator is a subset of Rn, and the subset can also be empty. So in these lectures and in our book, we will refer to this type of object as a set-valued operator, but there are other names used in other branches of mathematics and economics. So point-to-set mapping, that's one name. A set-valued mapping, multi-valued function, and correspondence. So correspondence is a terminology used more in the realm of economics. For notational simplicity, we'll use this matrix vector product like notation, Tx, to denote T parentheses x close parentheses. Okay, so if the output of the operator evaluated at x is a singleton, or if it is empty for all x, then we identify the set-valued operator t with a function, or we just say t is a function. We also say it's single-valued, and in that case, the domain of the function will be the input points x, such that the output of the operator is not empty. And when the output of the operator is a singleton, we write tx is equal to y, even though tx is equal to the singleton set containing y would be, strictly speaking, correct. So here we are overloading, and this will be a recurring theme. When we use set-valued operators, we will overload a lot of regular vector notation to sets in order to express a lot of notions concisely and, in my opinion, elegantly. We define the graph of the operator as follows. So the graph of the operator is denoted as GRAT, and it is the set of input and output pairs. So x is an input to the operator t, and then u is an element of the output set. And this is, of course, the subset of Rn cross Rn. Now, mathematically, the operator t and the graph of its operator is equivalent. So given an operator, you can define the graph of the operator. And given a graph of an operator, you can go back and define a corresponding set-valued operator as well. So these two objects are equivalent. And therefore, we often will not distinguish them. And in fact, we will not distinguish them. We will not distinguish them not just notionally, but also in terms of notationally. We will often write just the operator t when we really mean the graph of t. So sometimes we still will use the graph of t notation from time to time, but we will only do so when we want to expressly emphasize the fact that we are considering the graph of the operator rather than the operator itself. Let's make some further definitions. So the domain of a set-valued operator is written as dom t. It's defined as the input x's such that the output of the operator is non-empty. The range of the operator t is the set of outputs, and the output is defined as a vector within the output set of the operator for all inputs x. We also overload the function, the image of a set notation. So given a set C, the image of C under T is written as T taken as input C, and this is just the union of all output sets T where this small c belongs to the set big C. We define the notion. We also define the notion of the composition of multi-valued set-valued operators. So here, perhaps it would be more precise to put parentheses here. So T compose S evaluated at S is defined as T evaluated at S X. So note that this is composition of operators, but here this is image of Sx under T. Okay. And here this is further clarification. Okay. Next, we also define the sum of operators. So T plus S evaluated at point X, that's defined as Tx plus Sx. Now here, this sum, this is the Minkowski sum. And this is a set plus a set. Now, the composition of operators and the sum of operators can also be defined equivalently using the graph. So here, it would perhaps be more precise to say a graph of Ts and graph of T plus S, but as discussed before, we will often not distinguish the operator from its graph. So the graph of the composition of T and S is defined as the pair of input-output pairs. So X is the input, Z is the eventual output. So since we're composing T and S, Z is the output of the operator T, and X is the input to the operator S. And then there exists an intermediate output Y from S, such that when Y is provided as input to the second operator T, it produces Z. Here, the definition of the graph of the operator T plus S is as follows. So the input is X. X is provided as input to both operator T and S, and then we have Y plus Z. So Y is the output of the operator T, and Z is the output of the operator S. So here we define for set-valued operators, we define the domain, range, the image of a set, composition, and the sum. And these definitions, of course, when the operators are single-valued, it reduces to the standard notion of range, domain, composition, and sum, and image for regular functions. So this is in a way, these definitions naturally generalize these familiar notions to the case of set-valued operators. Okay, let's make some further definitions. The identity operator is a single-valued operator, and we write it as I. So I is a single-valued operator. It takes in as input X and then outputs x. But here, instead of defining writing the definition of I in as a function, here I instead directly defined the graph of this operator. So again, maybe it would be more precise to write graph, but again, we'll often not distinguish the graph and the operator itself. The zero operator is defined as the single-valued operator that takes in as input any point x, and always outputting the zero vector. And by the way, this is the zero. It's not the scalar zero. It's the zero vector in Rn. So when you're using these definitions, so in this class, not only do we overload scalars and vector notation, so you can so the zero can refer to the scalar zero or the vector zero. Not only when we do that, which is standard in regular linear algebra and applied mathematics, but we also heavily overload multi-valued and set-valued operations. So when you have an expression, it's important that you fully understand what the individual objects are and what the operations specifically mean. If you carry out operations in a careless manner, then you may encounter situations where the equation sort of looks fine, but things don't always work out. Okay, so in this case, t plus 0 is equal to t. T composed with I is t, and I composed with t is equal to t. But for example, t minus t is not always equal to 0. Okay, so so if you have a single-valued operator, then if the operator t is single-valued, then sure, t minus t is the zero function. But that's not always the case when you have a set-valued operator. So this is possible when t is set-valued. We say an operator t is Lipschitz if it satisfies this inequality. So this definition generalizes the notion of Lipschitz continuity to functions with a domain in Rn to operators without full domain. So the notion of Lipschitz continuity as it is usually defined and also as it was defined in the previous chapter requires the operator to have full domain and also for the operator to be not multi-valued. But in this case, we allow the domain to not necessarily be all of Rn. Now, if the operator t is L Lipschitz, so a priori, this is a set minus a set, and the norm, therefore, this is a set minus set, and then norm. So to be more precise, this is equal, this is defined to be equal to norm of u minus v, such that u is in tx and then v is in ty. So this would be this is the a priori the definition, and because t is a priori not assumed to be single valued, this is how we would define the left hand side. But when the operator t is L Lipschitz, then the operator is necessarily single valued, because if tx is not a singleton, then we will have if tx is not a singleton, then tx minus tx less than equal to L of x minus x would be equal to 0. So by the way, the meaning of this inequality is that because the right-hand side is just a single scalar, right? It's not a set. So the meaning of set less than equal to scalar, the meaning of this is this is defined as for all s in set, s less than equal to scalar. So the meaning of this inequality is that the left-hand side is a set and all elements within the set is less than or equal to 0. But all elements on the left-hand side are by definition non-negative. So this means that all elements on the left-hand side need to be exactly equal to 0. But this can only happen when Tx is a singleton. So therefore, when the operator T is L-Lipschitz, it is necessarily single-valued. We then define the operator inverse. So the inverse of the operator is defined most cleanly with its graph. So T inverse is defined as y comma x, where x comma x is an input-output pair to the operator T. So again, we're using, perhaps we should, we're mixing the operator and its graph, but yes, so we're defining the inverse of the operator as its graph. And the inverse of an operator is always well-defined, which contrasts with the situation with single-valued operators. Because if you have a single-valued function or a single-valued operator, then the inverse is only defined if it is a one-to-one mapping. And in other words, the inverse needs to be in some sense single valued in order for the inverse to be well defined in the usual case. But in this class, we're doing set valued analysis. And when we're dealing with set valued operators, the inverse is always well defined. So here's an example. Here we have the graph of an operator T. And in this particular case, the operator T is a single valued operator. At least it is so within this plotted region. Now the inverse of this operator is just the operator with x and y flipped. So in this 2D example, that means we mirror the graph along this 45-degree line. And if we draw the graph of T inverse, it looks like this. And because we make no requirement that the operator is single valued, T inverse is well defined. T inverse in this case is a multi-valued operator, and that's okay. By definition, the inverse of T inverse is equal to the operator itself, and the domain of T inverse is equal to the range of T. And conversely, the range of T inverse is the domain of T. However, we want to be careful with this following fact. The T inverse is not an inverse in the usual sense, because T inverse composed with T is not always equal to the identity, and in particular, T equals 0 is an example. Okay, so I urge you to think about this. What's the inverse of the 0 operator? I want you to think about that. And yeah, so give this some thought and try to think about what T inverse T is, and try to and make sure you understand why it is that it's not equal to the identity operator. Next, let's define the notion of a 0. So a 0, in the context of functions, single-valued operators, this notion of a 0 is often referred to as a root, but in this class we won't use the word root, we'll be saying a 0. So so for a given input operator T and a given input X, if 0 is contained in the output, we say X is a 0 of the operator T. And the set of zeros of an operator T is written as ZER-T. And that's just the set of, again, the set of X's such that 0 is within the output of the set Tx. Another way to express this set is via the inverse. So we write T inverse with the input 0. That's that is equal to the 0 set t, because let's put it this way. 0 is in tx if and only if t inverse 0 contains x. So the and then yes, so the t inverse 0, therefore t inverse 0 is set of x such that t inverse 0 in x, which is set of x such that 0 in tx. Many interesting problems can be posed as finding zeros of a multi-valued operator. In particular, many optimization problems can be posed. Many solutions to convex optimization problems can be posed as finding a zero of what's called a monotone operator. Okay, next let's talk about the subdifferential as an operator. So when a function f is convex, we define the subdifferential. And the subdifferential, now that we think about it, is a set-valued operator. So we provide as input a point x to the subdifferential, and then we get a set of subgradients. Given a function f, the set of minimizers of this function f is equal to the 0 set of the subdifferential operator. And when the function f is convex function f is differentiable, and when we know that a priori, or we assume that, then we will use the gradient operator instead of the subdifferential operator. Okay, so here's our first result regarding using the operator notation, and it's a very elegant result. When a function f is CCP, the subdifferential of f, the inverse of that is the subdifferential of f conjugate. Okay, so this is an important result. We'll be using this repeatedly throughout this class. So let's prove it. Okay, so in order to characterize the inverse relationship, let's consider input-output pairs. So x is an input to the subdifferential, and u is an output to the subdifferential set. Okay, so this is true if and only if. So we take, because u is not a set, right? U at this point, u is just a vector. So we take this to the right-hand side. So we have 0, 0 is in partial fx minus u. And by the way, we should clarify this is a set minus vector. So this is a set, but here we're subtracting it by a vector. And then if you think about this, well, this is equivalent to saying that x is an argmin of fz minus u transpose z. Why? Because if you take the subgradient of this convex function, subdifferential of this convex function, you get partial f, and then the z goes away, so you get minus u. So this is actually 0 being within this right-hand side is actually equivalent to the optimality condition of the optimization problem of minimizing this convex function. But then this optimization problem is somewhat familiar. So this optimization problem is the optimization problem that defines the conjugate function f star. In particular, the minimum, the infimum of this quantity with respect to z is equal to minus f star. So to put it differently, if we plug in the optimum of the minimizer x into this expression, which is this thing up to the sign flip, that is equal to the conjugate function f star evaluated at u. Okay, next we take this and we take this and put it on the right hand side, flips the left and right side, so you get f plus f star is equal to u transpose x. And then when the function f is CCP, Well, f is equal to f double star. So these two are equal under the assumption that f is CCP. And then finally, going from here, we take the argument backwards because now everything is symmetric in terms of u and x. So this whole chain of reasoning, starting from here, we arrived all the way to here. This can be reversed with the role of x and u flipped and with the role of f replaced with f star. And then when we do that, we get the inclusion x is in partial f star u. Okay, so through this chain of equivalences, we've shown that u is a subgradient of f at x if and only if f is a subgradient of f star at u. Okay, so that concludes the proof, and therefore we conclude that partial f and partial f star are inverse operators as multivalued operators. Next, let's talk about how to evaluate the subdifferential of the conjugate function. Define the convex function g as a function of y as the convex conjugate f star composed with a transpose. Here we assume that f is a CCP function, and we furthermore assume the regularity condition that the range of A transpose intersects with the relative interior of the domain of f star. Then, to evaluate the subdifferential, to characterize the subdifferential of the function g, we just write u is a subgradient of g at point y. And then, well, this holds if and only if u is a subdifferential of is a member of this expression. So why is this true? Well, this relies on this regularity condition. So as discussed in the previous, in the preliminaries chapter, this subdifferential is equivalent to this when this regularity condition holds. So basically the chain rule with subgradients, we can view this as the chain rule with subgradients, and the chain rule with subgradients holds with equality when this regularity condition holds. Now let's be careful in understanding what this expression means. So on the right-hand side, y is a vector, and then A transpose is a vector. And then partial f star evaluated at this vector. So this is a set, and then this is a matrix times a set. So this is a matrix set product. And this holds, well, so here we have u is a member of this thing. Well, that holds if and only if, because this is a set, right? So the partial f star, that's a set. So this holds if and only if there exists an x within this set such that u is equal to ax, right? So this inclusion, the meaning of this holds if and only if the second one holds. Now, we know that because f is CCP, partial f star is the inverse of partial f. So we take the partial f star, put it on the left-hand side, and we get this. So this holds. So we have this equivalence. Next, this is just a vector, so we can put this on the left-hand side and have this as a subtraction, and then we switch the left and right side. So we have 0 within partial fx minus A transpose y. And then again, this holds if and only if, because this is the familiar optimality condition of solving this optimization problem. Okay, so u is a subdifferential of g evaluated at y if and only if u is equal to ax, where x is the solution to the minimization problem of minimizing f of z minus y transpose a z. To put it differently, to find an element of partial g, we can obtain an element of partial g, a subgradient, by solving this minimization problem and then performing this matrix vector product with the solution with the minimizer x.